Now let's examine the simple harmonic oscillator and simple harmonic motion in general. A simple harmonic oscillator, by definition, is a device that provides an example of simple harmonic motion, which of course is cyclical motion, motion that is repeated over and over again. But the restorative force is from a spring or an elastic object of some sort. So the restorative force varies, and it's proportional to the displacement according to Hooke's law. So a weight on a spring would probably be the easiest example to think of and to visualize. Now, in Hooke's law, the restorative force, F, based on displacement in the x or y direction, would be minus kx, where k is the elastic force constant of the spring, and x is the displacement. And of course, the negative sign means that the force is always working opposite of the displacement of the object. In this case, we're looking at a vertical simple harmonic oscillator, but we get the idea that when the object is stretched downward, the spring is pulling upward, and when it's stretched up, compressing the spring, of course, is pushing downward. So the force is always acting opposite to the displacement. Now, hopefully from this graphic, we can see that there is a very strong correlation between simple harmonic motion and circular motion. Because the force varies with x, we have a varying acceleration as well, obviously. And that acceleration provides a varying velocity. The object, of course, would accelerate, decelerate, and come to zero. So you can see in our velocity position graph, if we were to plot position as a function of velocity, we see that we get a circular path, which is what we would call an orbit. So circular motion based on cycles per second or revolutions per second is very much correlated to simple harmonic motion. So many of the same concepts apply, such as frequency, represented by F or the Greek letter gamma, which is the number of cycles per second and is measured in hertz, a unit that simply means per second. And period, which is the time to complete one full cycle of motion, the standard unit of which is seconds. And frequency and period, you may remember, are reciprocals of one another. If you have one, you have the other. Now, if we were to plot a displacement versus time of a simple harmonic oscillator starting at the maximum point of displacement, we would get a cosine graph. The object would accelerate, decelerate, accelerate, decelerate, and so on and so forth. And that plot would come out to look exactly like a trig function graph, in this case, a cosine graph. Our equation derived from this graph would be the position as a function of time would be xm, the amplitude, times the cosine of the angle, which is the angular speed times time, plus the phase constant. We're going to define all these terms and hopefully make this a little clearer. Again, what we would call the angular speed, we are now going to refer to, since we're not talking specifically about circular motion, we're going to now refer to it as the angular frequency. And the angular frequency is different from frequency. Frequency is measured in hertz. Angular frequency applies the idea relative to circular motion, kind of cyclical motion would be a better way to describe it. And they differ by a factor of 2 pi. So very simply, if we have the frequency in hertz, multiplying it by 2 pi will give us the angular frequency in radians per second. And this is an important correlation we need to remember and pay attention to. Xm would be our amplitude, our maximum positive displacement, which is our definition of amplitude. And then theta in this case would be the phase constant, which is the position of the object at t equals 0 seconds. If the object, in other words, if we're not starting our timing, whether or not we're starting our timing right at plus x, the maximum positive displacement. Let's examine this concept of the phase shift a little more. Once again, our standard motion, standard equation for simple harmonic motion in the x direction. When we are talking about phase, we are talking about the angle over which the function repeats itself. And we define that as angular frequency times time, which would give us radians, plus theta, also measured in radians. And theta is the phase shift. The phase constant, that value theta, is the shift of the function if x does not equal x max at t equals 0. If it does, then theta is simply 0 and it drops out of our equation. Here's an example. In the black, you can see the graph of simply cosine of pi times t, a function. There is no phase shift because we are starting the graph at x max. The blue graph would represent a phase shift of pi over 2. And therefore our graph would look like an inverted sine graph, which of course is what the cosine of a theta plus pi over 2 graph would look like. In this case, our phase constant is 0, and in this case, our phase constant is pi over 2. So let's take a look at how we apply this in a problem. We have the graph of an object here is moving in simple harmonic motion as shown. The object has a amplitude, maximum displacement of 6.3 meters, and it's displaced 2.9 meters at t equals 0. So what must be the phase constant of this motion? Well, if we understand that our amplitude is 6.3, we can simply substitute into our graph that at the beginning of the graph, 2.9 equals 6.3 cosine of our angular frequency times 0, because we're talking about t equals 0, plus the phase constant. This brings us to some simple algebra. We divide both sides by 6.3 and take the inverse cosine of that 0.46, and we get two potential values here, 1.1 radians or 5.2 radians. We do understand that the cosine of theta is equal to the cosine of 2 pi minus theta. So therefore, that's how we end up with two potential answers, not just one, as our calculator would give us. Now, which answer do we want to pick? Because we look at our graph, and because the graph is increasing after t equals 0 and not decreasing, the graph is going up and not going down, then the correct value we would want to pick would be 5.2 radians. So with this equation for displacement for a simple harmonic oscillator, our equation for velocity can be found by taking the derivative. And of course, the derivative of the cosine would be minus the sine, so we would get minus a times the angular frequency sine of omega t plus the phase constant. Now, this gives us a convenient equation for maximum velocity of amplitude times angular frequency, because in a simple harmonic oscillator, the object will achieve its maximum velocity, obviously, when it crosses the x-axis. And the same is true for acceleration. So we can get an equation for maximum acceleration of amplitude times angular frequency squared. We'll use those equations very conveniently to solve some problems later on. The period of a simple harmonic oscillator can be derived in the following manner. We know the force acting, the net force acting on a simple harmonic oscillator would be mass times acceleration. So therefore, we would have negative m omega squared times x, and that would be equal to minus kx, as we have already looked at, since this is a simple harmonic oscillator, and therefore the restoring force follows Hooke's law. Solving for angular frequency then, we would get that the angular frequency will be the square root of the force constant divided by the mass. The period, therefore, would be the reciprocal of 2 pi, well, it would be actually 2 pi over the angular frequency, because it would be the reciprocal of the frequency, and the frequency would be the angular frequency divided by 2 pi. Substituting, we can then get the period is going to equal 2 pi times the square root of m over k. And this will give us the period for a simple harmonic oscillator, and we will test this concept in the lab. These next several slides in your notes contain sample problems for you to attempt. Stub your toes on and bring any questions you might have to class. The first one is pretty straightforward, but again, attempt them, bring them to class. We look at these problems, and this last problem will provide a little bit of explanation for. We have a block on a horizontal surface, a table, which is often called a shake table, that is connected to an oscillator that vibrates the table back and forth. And it vibrates back and forth with a frequency of 2.35 hertz. So the table goes from one side to the other and back again 2.35 times every second. The coefficient of static friction between the block and the table is 0.630. So we want to determine what is the greatest amplitude that this table can have if the block is not to slip along the surface. So we do want to remember, obviously, that if the block is not slipping and it is experiencing simple harmonic motion, then the maximum force acting on the object is going to be from our static friction. So if the maximum force is then going to be the mass of the block times the maximum acceleration. And if you recall, we did derive an equation for maximum acceleration of a simple harmonic oscillator dependent upon the frequency and the amplitude. This problem should not be too difficult for you to solve now, but again, if you have any questions, bring them to class.